Hello. Welcome to our video lecture.
Good morning, Team KC Conquers. Our task for today is learning about KSP and solubility equilibria.
Got it, Captain. What is the first task for today?
Let's go to the card swipe.
So KSP is the solubility product constant, and it is the equilibrium constant for the dissolution of an ionic solid. It's usually recorded at 25 degrees Celsius and has no units. This can be useful when you are looking at the dissolution of a salt. This reversible process can be seen in the example of solid silver chloride dissolving into its respective ions, and the ions are forming the solid at the same time. However, in the KSP expression, solids and pure liquids are not included, so it only includes the concentrations of the products. In the silver chloride dissolution, this means that the KSP expression will only include the concentration of silver ions and concentration of chlorine ions together. The higher the KSP value, the more soluble the substance is. Typically, when KSP is greater than 1, it indicates a more soluble salt. It's important to keep in mind that the expression shows us that the concentration of solute particles depends only on KSP. Even if water is added to or evaporated from the solution, this change in the volume of the solution itself does not affect the concentration of solute particles. KSP can also be used to predict if two solutions combined together will form a precipitate. You compare KSP with QSP, where QSP is the same as KSP, except it describes the solution at any given point in time. Remember, KSP describes the solution at equilibrium. So if QSP is greater than KSP, a precipitate will form, but if QSP is less than KSP, a precipitate will not form. On the other hand, solubility describes how likely a solute will dissolve in a solvent to form a solution. The solubility of ions in a reaction will always be the X value in your ICE table. Solubility is described in units of moles per liter, which is molarity, or it can be described in grams per liter. And to compare KSP and solubility, they are two very different things. Solubility directly refers to a saturated solution, and this is where the solution contains the maximum amount possible of solute to dissolve in a certain amount of solvent at a certain temperature. The biggest difference you'll find is that is with the units, where KSP has no units at all. And regarding the relationship between these two, given KSP, you can determine the molar solubility of a substance, and given the molar solubility of a substance, you can determine KSP.
I'm not precipitating any judgments, but KSP is pretty important in every saturated solution.
Great, thank you, reciprocal and oxygen magnesium.
Now on to the next task, understanding graphs.
So for the first graph, adding more solids to the solution increases the concentration of the solution very quickly. Then the reaction function Q will be greater than KSP to precipitate parts of the salt. And finally, the concentration of ions in the solution will gradually decrease until the reaction reaches equilibrium. The second graph shows that the solubility of a substance decreases when the solution already contains one of its ions. The solubility of the salt in pure water is greater than its solubility in a solution containing common ions. For the next picture, after some of the water evaporates, the volume of the water changes, but the solution remains saturated. If the temperature is constant, the KSP will not change, so the concentration of the solution will not change. For this graph, if Q is greater than KSP, the reaction will shift to right because the concentration of ions in the solution is greater than the solubility precipitate. So the precipitation occurs if the solution is unsaturated and Q is less than KSP, indicating that more solids can be dissolved until equilibrium is reached. Let's look at the last picture. According to the graph, the solubility is related to the temperature, which means that KSP is related to temperature.
What was the charge when NaCl was arrested? A salt.
Okay, thank you, oxygen magnesium. Now on to the next task. The first question we have is at 25 degrees Celsius, the value of KSP for PbCl2 is 1.6 times 10 to the negative 5, and the value for KSP for AgCl is 1.8 times 10 to the negative 10. Part 1 asks if 60 milliliters of 0.0400 molarity NaCl is added to 60 milliliters of 0.0300 molarity PbNO32, will a precipitate form? Assume that the volumes are additive. Show calculations to support your answer. So based on the equation, we can tell that PbCl is a precipitate that's formed by the combination of two substances, and it dissociates as the following in water. In order to determine whether precipitate would form, we need to find QSP and compare it with KSP. We know that QSP equals the concentration of the aqueous ions in PbNO32 and NaCl. Since both of these compounds contain snap ions, we know that they fully dissolve in a solution, dissociate in a solution. Because Cl is in a 1-to-1 ratio with NaCl and Pb, it is also in a 1-to-1 ratio with PbNO32. So we are able to multiply the volume molarity for each compound to find the mole amount. Multiplying these gives us 0.0024 moles of Cl minus, since we added 60 milliliters of each solution. And the total amount of volume present in the solution is 120 milliliters, or 0.120 liters. To find the concentration of Cl minus, we divide the moles by liters to get 0.020 molarity. Doing the same for Pb2 plus, multiplying liters by molarity, we find that there are 0.0018 moles of Pb2 plus in solution. Dividing that by 0.120 liters, we get a concentration of 0.015 molarity for Pb2 plus. From there, we can multiply both the concentrations to find Q, which would be 0.015 times 0.020 squared to get 6 times 10 to the negative 6. And we know that KSP value is 1.6 times 10 to the negative 5, which is greater than Q, therefore no precipitate will be formed. And on to part 2, which asks calculate the equilibrium value of Pb2 plus in 1 liter of saturated PbCl2 solution, to which a 0.250 mole of NaCl has been added. Assume that no volume change occurs. So since we already know the KSP and its formula, we can manipulate the equation to find Pb2 plus concentration. Since Cl is present in a 2-to-1 ratio in PbCl2, we need to square it in the KSP expression. Manipulating the equation, we get 1.6 times 10 to the negative 5 or 0.250 moles of Cl because Cl is a 1-to-1 ratio with NaCl. And then we square it for the PbCl2 formula. Doing this, we find that Pb2 plus concentration is 2.6 times 10 to the negative 4 molarity. And lastly, the third part asks if 0.100 molarity NaCl is added slowly to a beaker containing both 0.120 molarity AgNO3 and 0.150 molarity PbNO3 at 25 degrees Celsius, which will precipitate first, AgCl or PbCl2. Show calculations to support your answer. To solve this, we need to find the concentration of Cl- for both solutions and compare the amount. Let's start with AgCl. This is the KSP formula for AgCl. We know that it is equal to 1.8 times 10 to the negative 10, according to the information given prior in the question. And manipulating the equation again and subbing in the 0.120 molar concentration of Ag plus, from the question, we get 1.5 times 10 to the negative 9 molarity for Cl- in AgCl. And for PbCl2 solution, this is a KSP equation. When we manipulate this, we need to take the square root of KSP over Pb2 plus concentration to account for the Cl squared in the KSP formula. Plugging in the 0.150 molarity from the question, we get 1 times 10 to the negative 2 molarity for Cl in PbCl2. Since you can see that Cl concentration in AgCl is less than the Cl concentration in PbCl2, Cl will reach the lower concentration first, meeting the criteria to form a precipitate. Therefore, AgCl will precipitate first. And finally, a chem joke to end our video lecture.
Why did the chemists break up with their partner?
Because they couldn't find any common ions.